Our project is revolved around thermal remediation methods. This presentation will break down what thermal remediation is and how it is used in contaminated sites. The agenda for this presentation includes the physical mechanisms of thermal remediation, factors that may positively or negatively influence the effectiveness of thermal remediation, how the processes are implemented in the field, some case studies where thermal remediation was used, the applicability and limitations, and lastly, the cost and availability of using thermal remediation. So first, we'll just start with just a general high-level description of what thermal remediation is. Thermal remediation is the application of heat or energy to remove contaminants from a contaminated medium. Applying heat to the contaminants will allow the COCs, or contaminants of concern, to be volatilized or evaporated in the subsurface by increasing vapor pressure. For all types of thermal remediation, there will be a vapor and liquid extraction system set up so that the volatilized contaminants can be safely collected for further treatment, whether it be using some sort of granulated activated carbon or maybe some sort of air stripping to absorb the COCs. So the first type of thermal remediation we will cover is thermal conduction. Thermal conduction includes the use of heating elements, which is usually heater wells, in the subsurface to heat the surrounding area that includes the contaminants. The heat will then dissipate conductively through the soil, which will then reach the target contaminants eventually. The heat will cause the contaminants to vaporize, which makes them much easier to capture and treat, and then to extract the contaminant vapors, screened vertical vapor extraction wells, or VEWs, or multi-phase extraction wells, MPEs, are set up. Here we have some graphics that are related to thermal conduction remediation. Conduction is the transfer of heat through a material by direct contact, and in this first graphic, the burner is providing heat to the frying pan through direct contact, and then the frying pan as a result is heating the food through direct contact as well. So in our situation with thermal conduction, the heater wells act as the burner or source of heat, which will heat up the surrounding soil that is making direct contact with. The next graphic then just depicts a typical grid pattern that extraction wells will be set up in. The thermal conduction heaters will be usually set up in some sort of hexagonal pattern with occasional temperature monitoring points, which are pretty important, and then extraction wells, which are usually located somewhere in the middle of these hexagons. The next type of thermal remediation that we will cover is electrical resistance heating. The key principle that electrical resistance heating utilizes is the electrical resistance of the contaminated soil. Electricity is applied from some outside source to the electrodes that are located in the pattern so that the electricity is able to pass through the soil from one electrode to another. And three-phase AC or alternating current is used to power these electrodes typically. The voltage difference between the phases drives the current flow through the soil. So the amount of current that is conducted by the electrode which passes through the soil is based on the electrical conductivity of the soil. The larger the electrical conductivity, the more current flow, which will lead to more heating. The way that the soil heats up from the current flow is based on the electrical resistance. As energy is conserved, the kinetic energy of the electrons moving from the current flow are then met by the soil and resisted, and that kinetic energy is then turned into heat energy. As the electrical conductivity is dependent on soil moisture content, the soil cannot be completely dried out. Electrical resistance heating is usually limited to 100 degrees Celsius because of this. And then once the heat from the electrical resistance builds up and vaporizes the contaminants, um, the vapor contaminants are then extracted. So here we have two graphics relating to electrical resistance heating. The first graphic just gives a good illustration of the typical grid pattern of electrical resistance heating. As you can see with the A, B, C, there are three phase patterns that are usually used. And then typically in the middle of these triangles, you have an extraction well. And then the next graphic just gives a good overall representation and process of how electrical resistance heating actually works. So you have some sort of electricity coming in from this power distribution system, and then that is connected to the electrodes at the actual contaminated site. And here you can see the electrodes are set up in a triangular shape with the extraction well in the center of them. And then there's also a temperature sensor, which is necessary so that one would know if the temperature of the subsurface is getting close or above 100 degrees Celsius, which is kind of that parameter. The extraction well is then connected to some sort of treatment system. In this graphic, the contaminant vapor is either treated by being released to the atmosphere or it's sent for water treatment, and then that is discharged to somewhere safe. So the last type of thermal remediation that we will cover in this presentation will be steam-enhanced extraction. So steam-enhanced extraction is based on the method of injecting steam directly into the subsurface. Steam is injected in depth screen intervals of 1 to 3 feet, but it'll typically just be 2 feet. The steam will initially move radially around the well, and this forms a condensate front that provides heat and energy to the soil. And as more and more steam is pumped, a steam zone will form around the steam injection wells, which will then just push out to the extraction wells. And then the heat provided from the steam volatiles the contaminants, which makes it easier to extract. And then a network of multi-phase extraction wells, or MPEs, are used to extract these vapors. So this diagram is another good representation of what a typical steam-enhanced extraction project may look like. So here you have your initial steam generator, which will just pump steam into the steam injection wells. This heats up the subsurface and makes it easier for the volatile contaminants to be extracted over time. You then again have some sort of treatment system connected to the extraction wells, and then the contaminants may either be treated to be released to the atmosphere or pumped and then treated with water to be discharged safely somewhere. So next we have influencing factors of thermal remediation. These may include factors that may increase the productivity or efficiency of thermal remediation, or in some situations where thermal remediation might not be the best choice out of all the remediation methods. So thermal remediation is best used for organic contaminants, and these might include things like VOCs, volatile organic compounds, chlorinated VOCs, or semi-volatile organic compounds. And they're also thermal remediation is also useful to capture NAPLs. And then in a location with high permeability, steam enhanced extraction is the best thermal remediation choice. So in aquifers with high permeability, contaminants are able to move more freely through the subsurface, and the injection of steam increases the mobility of these contaminants even more by reducing their viscosity. The steam will then also be able to move at a faster rate in areas with high permeability, and um, the faster the steam moves, the faster the extraction of the volatile contaminants. So for areas with low permeability, usually thermal conduction or electrical resistance heating will be used. So aquifers with shallow contamination are very ideal for thermal remediation for a couple of reasons. Lots of the treatment equipment that have to be installed into the ground um, leads to lots of timing and work needed to do so. So having contamination that is not deep is extremely beneficial. And then additionally, less energy will be needed if the contamination is shallow, um, due to the fact that heat takes a while to spread. So uh, the less deep the contamination is, the less time it would take for the heat to build up in the subsurface. And then less energy requirements means less expenses as well, making it more profitable for whoever's cleaning up the contaminated aquifer site. Um, Sites with consistent stratigraphy are ideal for thermal remediation because of mainly just planning procedures. It's just much simpler to plan for a geographical location where the layers of the earth and certain features are known, especially in this case where you're working with the subsurface of sites. So for any site that may require the temperature of the subsurface to be above 100 degrees Celsius, thermal conduction can be used because the heating wells can reach temperatures of 1400 degrees Fahrenheit, which equates to around 760 degrees Celsius. Also, any subsurface that's accessible is also ideal. And all in all, thermal remediation is just relatively effective in most situations.
All right. So next we have the negative influencing factors, and they are safety, operating costs, physical characteristics, and contaminant characteristics. Safety and operating costs are probably unanimous throughout all of these treatment techniques, but physical characteristics and contaminant characteristics can be more tailored to thermal remediation. So next, so safety and cost. So with thermal radiation, electrocution, scalding, pressure ruptures, and energy and electricity are safety and cost factors. So electrocution from electric heating and elements or electrodes, workers on the working above ground and get tangled with them or handle them misproperly. Next is scalding and pressure ruptures. So we're working with steam in some of these remediations. And if down in one of the wells, pressure builds up, clogs up a pipe, and up top, it ruptures by a worker, they can get scalded from the steam or just hurt from the pipe rupturing in general. As far as energy and electricity, electricity can be expensive, and these are pretty energy intensive systems. They require a lot to either put the electricity down or heat. It takes a lot of energy. And if you're in a remote area, you might have to make this yourself with a generator, and fuel costs can be quite expensive. So physical characteristics, soil type, depending on the thermal conductivity, it can be difficult to heat the ground to the correct temperatures. One of our treatments is thermal conductivity, so that would be a major issue. Would not suggest using that one. Next is geology, so the ability for the fluids and vapors to travel through the medium to be removed. Um, Things like porosity, permeability could play a major factor in if this a specific treatment is worth it or not, and actually um, able to work. Next is contaminant characteristics. So things like the boiling point, viscosity, concentration. This can all affect if and what methods to use. Um, so boiling points can affect the contaminant is cleaned or just completely destroyed when it's heated. So if it's just made into a boiling and vapor, it can be extracted. But if it's destroyed, it'll be broken up into different parts. Depending on regulations, what you're trying to achieve, this could be good or bad. Viscosities, and how they move through pores, if it's easier or harder to do that, and what temperatures they're needed to reach to get a viscosity that will actually move through the medium. And then concentrations could affect how much, the temperatures, how long you have to do this. If it's really concentrated and you need to do it a lot, that can have a major cost implication. And then movement within the soil. So these are very well engineered systems, but accidents can happen. Say some of the contaminant gets through and goes past an extraction well and out of the remediation zone and gets into an aquifer that takes it downstream. That could be a very negative implication and cost a lot for the company to fix. So as far as field implementation goes, we have three techniques. So the first technique is thermal conduction heating, or TCH. The next one is electrical resistance heating, or ERH, and steam enhanced extraction, or SEE. And right here you can see three examples of them, and this is what you see above the ground and not what's going on in situ in the ground itself. So our first one is thermal conduction heating, or TCH, and this is when heat is applied with conduction through metal rods that are put, or metal um, wells are drilled, and then metal or something is put into the ground, and heat is directly transmitted from those metal put in the ground through grain to grain in the soil, so it radiates out. The temperature goals for this treatment can range from 100 to 325 degrees Celsius, depending on the contaminant. So installation for this consists of installing heaters and vapor extraction points. Uh, the extraction points vacuum contaminant out of the area. So I think you can see my cursor. If not, the red is the heater, and as you can see, the red is going out, conducting throughout the ground and heating up these contaminants, which will then be sucked off into these wells and removed. Um, so if there is a really well insulated soil that you can't heat well with the desired length between heaters, you can add extra layers just to get that correct temperature. Because one of the advantages of this treatment is it's very consistent over the area. It can be a large area or a small area. Um, so that temperature control is very important. It's also good for a wide variety of soil types, including gravel, clay, sand, and tight soil layers. So as we discussed earlier, that permeability and porosity doesn't have to be very open for this to work because it heats everything and then sucks it out. Um, and this also doesn't have to be saturated. You can do above or below the water table. Okay, so this is a skeleton of what the system will look like. On the left, it starts with the power distribution going to the pad where all of the wells and heaters are. They go down, and then the contaminants brought up out of the soil and then put through the top process there, which is above ground, and that treats it um, so it can be disposed of. So next, we have electrical resistance heating, or ERH. This passes electrical current through the ground in either 3 or 6 phase electrical heating. It can be a triangle pattern or hexagonal pattern. Um, Electrodes can be spaced anywhere from roughly 8 to 40 feet apart. And this can be used with large or small areas. Sometimes you have to worry about dead zones, but if it's correctly set up, that should not be an issue. So how this heats is resistance to electrical current, heats the soil and boils portions of the water, which can then be removed. The ideal resistance from the soils to get this to work is roughly between 5 to 400 ohm. This does require water in the soil, so that could be a limitation. You might have to inject water into the soil. Sometimes the electrodes, they just pump water through them, so there's always water there, which allows the electricity to be conducted throughout the area where this is occurring. It can take 2 weeks to reach the boiling point of water, which is what this system is designed to do. Um, because as the water heats up and evaporates in the conductive zones, it makes that contaminant also heat up and ideally become a vapor, and then it can be removed. Um, One way that this system does, like a specialty of this system, is it requires isolation transformers, and they are used to ensure that the current is only applied between electrodes and doesn't shoot off out of the system and potentially harm something out of the system. And then the steam is what is generated and carries the contaminant to the extraction wells so they can be taken up. In this picture, you can also see the electrodes here, and the red lines between the drill down electrodes is the current passing through, which can heat and remove the contaminants. And here is a skeleton diagram of this system as well. Power, uh, the electric, excuse me, the electrodes down and the extraction well in the center, and then it is brought up and treated just like the last system. The last system here is steam enhanced extraction, and this uses the direct injection of steam into subsurface through wells. This can be done either vertically or horizontally. Um, Usually each location can be different, but the steam can be injected in intervals roughly 2 feet. Um, this, when the steam is injected, it heats up the contaminant, and usually the contaminant becomes a vapor. Um, and the so for this system, energy is usually created on site instead of from the electrical grid. What the steam does is the steam pushes contaminants toward the extraction wells by creating a pressure gradient as it's pushed out of the pipes that are brought down into the ground, and it pushes them towards extraction wells. As you can see, the red is the steam being pushed. It's pushing contaminant toward these extraction wells. This will work in saturated or unsaturated zones because the steam will be pushed in and push whatever's in the ground towards the wells. Liquid phases with boiling points less than water are almost completely removed in this method because the steam heats them up and it can be easily removed. But usually this is for contaminants with a boiling point less than 175 degrees Celsius. They might not be completely volatilized, but they can still be extracted. This is best with permeable geologies that allow the steam to penetrate, thread through the rock, and push the contaminants out towards the wells. So this is kind of the skeleton figure for this system. You can see the steam generator is on a trailer here because it's made on site most of the time. Again, they're placed in the ground, the steam is inputted in the system, and it pushes it towards extraction wells where it's brought up and then treated on the surface. A lot of the time, the surface treatment will be with like a granulated activated carbon, where the contaminants run through it, and then the vapors are released to the atmosphere. The water can is treated as well and can be discharged or potentially taken off site if it needs more, as well as the contaminant itself is removed and disposed of. All right.
In this section, we will go over applicability and limitations for the 3 different types of thermal remediation methods. First, we'll go over thermal conduction heating, or TCH. Let's start by looking at the characteristics that may limit the use of TCH. Soil composition is one of the factors that affect the effectiveness of TCH in soil composition. Soil materials with high conductivity, such as clay or rock, can inhibit the propagation of heat, potentially reducing treatment efficiency. Energy consumption, since TCH requires significant energy inputs to maintain elevated temperatures throughout the treatment process. This can lead to a high operational cost, especially for larger or deeper contamination zones. And slow treatment rates, because compared to other thermal methods, TCH may have relatively slower treatment rates. This is particularly evident in situations where heat distribution is uneven and where there are barriers to heat transfers within the subsurface. Now let's look at the characteristics that make TCH a useful remediation method. Versatility, since TCH is applicable to a wide range of contaminants, including volatile and semi-volatile organic compounds, as well as certain metals And this versatility makes it a valuable option for addressing various types of concentration contaminations. Next is the depth of treatments. TCH can effectively treat contaminants at various depths within the subsurface. Whether dealing with shallow or deep concentration scenarios, TCH offers flexibility and efficiency in remediation efforts. And lastly, one of the significant advantages of TCH is its capability of in situ treatment. This means that the contamination can be remediated without the need for excavation, minimizing site disturbance and reducing costs associated with soil handling and disposal. In conclusion, while thermal conduction heating presents certain limitations such as soil composition, constraints, and energy consumption concerns, its versatility, depth of treatment, and in situ capabilities make it a valuable option for addressing contaminated sites. Now we will display a quick visualization of the thermal conduction heating.
Such as electrical thermal conductive heating. Electrical heater wells are installed in the contaminated subsurface. Only heat is applied to the subsurface using renewable energy. The heat spreads by thermal conduction below and above water table and is almost uniform for the entire range of soils. The technology works in geologies ranging from gravel, sand, clay, all the way to solid rock like granite to any depths. Thermal conductive heating technology is the only in situ heating technology that can reach temperatures at several hundred degrees Celsius and can thereby treat any kind of organic contaminants with low to high boiling points like gasoline, chlorinated solvents, all the way to PCB, dioxins, and even mercury. Contaminants are vaporized according to their boiling point temperature and extracted to the surface, vacuumed, and treated in an above-ground treatment process. The heating process typically lasts 3 to 6 months, depending on contaminant type and concentrations. At the end, almost 100% of the contaminants are removed by electrical thermal conductive heating technology.
Now we go on to electrical resistance heating. Electrical resistance heating has very similar applications and limitations to TCH, starting with characteristics that limit the use of method. Soil conductivity, since ERH may be less effective in soils with high electrical conductivity, as it relies on the passage of electrical currents through the soil to generate heat. In such cases, additional amendments may be required to enhance conductivity and improve treatment efficiency. Energy consumption, since ERH requires significant energy inputs to sustain elevated temperatures, leading to high operational costs, particularly for larger or deeper concentration zones. And lastly, electrode installation. The installation of electrodes for ERH can be complex and time-consuming, requiring careful planning and expertise to ensure proper placement and configuration. The characteristics that make the method useful are the depth of treatment as well. ERH is effective for treating contaminations at various depths within the subsurface, including shallow and deep concentration zones, which is very similar to the TCH method. Uniform heating. ERH can achieve relatively uniform heating at the subsurface, ensuring thorough treatment and improved remediation efficiency. And lastly, it's also an in situ treatment, just like the TCH. The ERH can be applied in situ, minimizing site disturbance and reducing those costs associated with excavation and the soil disposal. So here's a quick visualization that explains how ERH works.
This animation illustrates in situ thermal remediation of chlorinated volatile organic compounds in soil and dolomite bedrock using TRS electrical resistance heating. 4 contaminant source areas partially below buildings were remediated in 2009. The results of one of the source areas are in this animation. The red mass represents the contaminant. The vertical black rods are the ERH electrodes that were co-located with recovery wells. The electrodes deliver energy into the subsurface and convey steam and vapors to the surface for treatment. The electrodes do not get any hotter than the surrounding soil. The days of operations and contaminant mass removed are in the upper left and right corners of the animation screen. Subsurface temperature increases slightly faster in the areas of highest contaminant concentrations. This is advantageous because these areas clean up quicker and can be turned off early following sample confirmation. The remaining energy is redirected into the areas until they are cleaned up also. This eliminates wasted energy and saves time and money. Average subsurface temperatures increased at a rate of 1.5 degrees Celsius per day during heat up, and the maximum subsurface temperature reached was 114 degrees C. At the end of ERH, final contaminant concentrations were orders of magnitude lower than the guaranteed remedial goal. Confirmatory soil sampling included independent analysis of 204 soil samples collected from 71 sample locations. Over the 6-month ERH operating period, 600 pounds of contaminant mass were recovered. The contaminant mass was reduced by 98.4%.
To finish the applicability and limitation section, we will go over characteristics of steam enhanced extraction, or SEE. Characteristics that limit the use of the method involve energy consumption. SEE requires significant energy inputs for steam generation, particularly for larger and deeper contamination zones, leading to a high operational cost. Depth limitations as well. The effectiveness of SEE may be limited by the depth of concentration, as steam penetration may be insufficient to treat contaminants located at significant depths within the subsurface, and the potential of mobilization. There are risks of mobilizing contaminants during the steam injection process, particularly if they are volatile or mobile, which may we may need an additional contaminant or treatment measure to prevent off-site mitigation. Characteristics that make the method useful involve contaminant type. SE is effective for treating a wide range of contaminants, including volatile and semi-volatile organic compounds, as well as certain metals. Enhanced mobilization. SE can enhance the mobilization of contaminants by increasing their vapor pressure or solubility in groundwater, facilitating their removal from the subsurface. And it's also an in situ treatment. SE can be applied in situ, minimizing site disturbance, as well as reducing those costs associated with the excavation and soil disposal, which we talked about previously. To conclude the presentation, we will be discussing the cost and availability for each thermal method. So starting with the thermal conduction heating, the cost of implementing TCH typically ranges from $100 to $200 per cubic yard of soil treatment. Factors that can influence costs include the depth and extent of contamination, the type of heating system used, energy consumption rates, and site availability. Companies that provide TCH are TerraTherm, Temco Electric Heating Corporation, and Hammers Technology. This table displays the implementation costs for small, medium, and large volume TCH projects. As you can see highlighted in green, the total costs range from $3 million to over $22 million US, and have a range of US dollars per cubic meter of 90 to 200. As for the electrical resistance heating, the cost of implementing the ERH is generally lower compared to the TCH system, ranging from $32 to $73 per cubic yard of soil treated. Factors influencing the costs are similar to the TCH. Factors such as contamination levels, soil conductivity, electrode configuration, energy consumption rates, and site-specific conditions can influence the cost. Companies that provide ERH are TerraTherm, Watco, and Polonis Technologies. This table displays the summary costs of ERH applications from a recent Navy project for treatment of source zones containing DNAPL or high concentrations of volatile contaminants. As you can see, the total cost of this project was approximately $1,274,000. For the steam enhanced extraction, cost estimates ranges from $50 to $300 per cubic yard, depending on site characteristics. The most significant factor influencing costs is the number of wells required per unit area. This is directly related to parameters like geology, permeability, and depth of contamination. Shallow contamination requires closer well placement and lower operating pressures to prevent soil fracturing. Deeper contamination requires farther well spacing and higher operating pressures. These differences in contamination depth show that fewer wells could be used depending on site geology, which would lower capital costs. Unfortunately, it was more difficult to find specific examples of the cost implementation for the steam enhanced extraction. However, based on similar influencing factors to other remediation methods, it can be assumed that the cost calculation process would be about the same, except for the SEE cost range. Companies that provide the steam enhanced extraction services are TerraTherm, TRS Group, and Geo Environmental Remediation Company. Thank you very much for watching our presentation. Please take time to fill out the corresponding quiz, and thank you for your time.
Now we will move into the demonstration level section where case studies will be highlighted for each of our 3 thermal remediation methods. Our case study for thermal conduction heating is about the Midler Crossing brownfield site in Syracuse, New York. The thermal remediation company TerraTherm implemented thermal conduction heating in order to clean up the site for pioneer companies. Midler Crossing was used as early as 1866 by Pierce, Butler, and Pierce in the manufacturing of boilers and radiators. Then, in the 1920s, the Prosperity Company manufactured industrial laundry and dry cleaning equipment on the site. From these industries, chemicals were disposed of on this land, making it a brownfield site. It is contaminated with chlorinated solvents, including perchloroethane and trichloroethane. The approach to this project was to first install TCH heaters to a depth range of 23 to 30 feet to heat the target treatment zone to 100 degrees Celsius. TerraTherm installed 25 horizontal vapor extraction wells beneath an insulated vapor cover to ensure air pressure control and effective extraction of steam and COC vapors above the shallow water table. Challenges encountered were moderate to high groundwater velocities within the fill, and underlying rock and soil required installation of a sheet pile cutoff wall. The performance of the remediation was documented by samples from 51 locations. At the end of the project, all areas met the cleanup standards after thermal treatment. Currently, the site is redeveloped in the location of a large home improvement store and a federal credit union. Our case study for electrical resistance heating is about the ICN Pharmaceutical site in Portland, Oregon. This site was used as a clinical laboratory from 1961 to 1980, and during that time, the lab used a variety of organic and inorganic compounds with wastes from operations being disposed of in a dry well about 20 feet deep. Results of groundwater investigations at the site identified the former dry well as the source of groundwater contamination, with contaminants being VOCs including TCE, DCE, VC, benzene, and toluene. The site geology consists of overbank with silts and sands interlaced throughout, while the water table is encountered at about 8 feet deep. Troutdale Gravel Aquifer, or TGA, underlies the overbank formation, and consists of unconsolidated and cemented gravels of the Troutdale Formation. The TGA is approximately 175 feet thick in the site area. The ERH system at the site was operated from May 2000 to December 2001. The initial ERH system consisted of 60 electrodes installed to a depth of 58 feet, placed in hexagonal arrays. In the boreholes where the electrodes were, steel shot was packed to improve conductivity and increase the effective diameter of the boreholes. Additionally, impermeable seals were placed in the annular spaces to prevent hot vapors and liquids from escaping through the boreholes. Each electrode was capable of directing power to the three zones in the overbank: the 20 to 30 foot, 34 to 44 foot, and 48 to 58 foot. The system was monitored using 13 subsurface pressure monitoring points and 8 subsurface thermocouples. The initial heating was limited to the bottom interval, 48 to 58 feet, to establish a hot floor and prevent downward migration of contamination. When the ERH remediation area was expanded in December 2000 and May 2001, electrodes were placed within close proximity to the security fence that surrounded the perimeter of the ERH remediation area. A soil vapor extraction was also implemented. The figure on the screen shows the location of the shallow, intermediate, and deep monitoring wells at the site relative to the area that was treated. This table on the screen shows the maximum groundwater contaminant concentrations before treatment when the ERH system was shut down December 2001 and 6 months later in June 2002. As of December 2001, maximum groundwater contaminant concentrations in the overbank area had been reduced from 150,000 micrograms per liter to 100 micrograms per liter for TCE, from 370,000 to 1,300 micrograms per liter for DCE, and from 24,000 to 50 micrograms per liter for VC. Through June 2002, TCE concentrations decreased to 8.11 micrograms per liter, while DCE and VC concentrations were unchanged. The concentrations of all three contaminants were above Oregon's MCLs. When ERH was completed in December 2001, VOC concentrations in groundwater had been reduced by more than 99%. The data strongly suggested that the remaining groundwater contamination would likely be addressed by an active microbial population, and biosparging was implemented. Monitoring results from April 2005 indicated that VOC concentrations were slightly above MCLs in a few wells in the overbank layer, and in one well in the TGA layer, and that in general concentrations appeared to be declining. Based on these results and the determination that remaining groundwater contamination based on these results, the determination is that remaining groundwater contamination does not pose a significant risk by either human ingestion or to ecological receptors. Our case study for steam-enhanced extraction is about Area A of the northeast site at the Young Rainey Star Center in Largo, Florida. In the late 1960s, drums of waste and construction debris were disposed of in a swampy area of the northeast site. The site was contaminated with around 5,500 pounds of NAPL constituents, such as trichloroethylene, cis-1,2-dichloroethylene, methylene chloride, toluene, and petroleum hydrocarbons. Steam was used to deliver energy at high rates to the surficial aquifer, both inside and outside of Area A. Electrical resistance heating was also used, but this was to heat the Hawthorne Group clay layer, to preheat the perimeter of Area A prior to steam injection, and to deliver energy to a relatively low permeability sand zone located between 3 and 6 meters, or about 10 to 20 feet deep, within the surficial sand aquifer. At the onset of operations, the well field for Area A consisted of a network of 66 operational boreholes and 44 monitoring locations. So on the figure on the screen, you can see 15 steam injection wells around the perimeter of Area A, 28 extraction wells with electrodes between the screened interval to heat the Hawthorne Group and the base of the surficial aquifer, 21 combined steam injection electrode wells to heat the surficial sands, 2 deep electrodes to augment Hawthorne Group heating, added to improve the 3-phase electrical heating coverage, 36 temperature monitoring boreholes equipped with thermocouples at about 4 feet, with about 4 feet vertical spacing, and 8, so 4 pairs of groundwater monitoring wells installed outside Area A. Electrodes were placed in both injection wells and extraction wells. This design was chosen in order to optimize the heating and minimize drilling and construction costs. Steam was generated from softened water using a diesel-fired boiler system with 4 units. Steam was piped to the injection wells using steel pipe, and the pressure was regulated at each wellhead. Steam flow rates were measured for each injection interval using orifice plates with differential pressure gauges. Operations lasted 4.5 months and followed a strategy where contaminant spreading was minimized and recovery was maximized. Vaporization rates were increased drastically by conducting pressure cycling from mid-November until cessation of heating in February. In each cycle, the site was heated until steam flow from the extraction wells was steady, at which time a depressurization cycle was initiated. Slowing the steam injection rate reduced the pressure in the formation, leading to boiling of some of the pore water and chemicals present in the treatment volume. Within a few hours of slowing the steam injection, vapor phase PID readings on V1 samples typically increased by orders of magnitude, indicating that boiling of pore fluids in the subsurface had led to vaporization of large amounts of contaminants. The figure on the screen shows the relation between the steam injection rate and the calculated VOC removal rate in the vapor stream at the V1 sample location. Increases in the mass removal rate correlate with times when the steam injection rate was decreased, as shown by the vertical lines on the figure. An estimated total of 2,500 pounds of VOCs were recovered. The available data are insufficient to allow for estimation of the recovered total petroleum hydrocarbons in the mass in the vapor stream, however.